You know, we tend to treat mathematics as this like ultimate objective reality.
Right, like a universal truth or something.
Exactly. Like if you write out a formula on a chalkboard, the answer is universal. It doesn't matter who solves it. The math just remains the same.
Yeah, you'd think so anyway.
But when we actually look at software engineering, that illusion of perfect objectivity just completely falls apart.
Oh, absolutely. It shatters.
Because the way we choose to actually tell a computer to do the math can fundamentally alter the outcome, and sometimes in pretty terrifying ways.
Which is exactly what we're looking at today.
Yeah, so today we are taking a deep dive into this absolutely fascinating 2026 benchmark project. It was put together by a developer who goes by the handle Luck036.
Right. And to be clear for everyone listening, this is not just, some dry execution speed test for programmers.
No, not at all. It is basically a detective story.
Yeah, it's a polyglot detective story, which is what makes it so incredibly unique. The whole premise was taking one specific, highly complex mathematical algorithm and writing it out in three entirely distinct programming languages.
And those were Python, C++20, and Rust, right?
Exactly. Those three. We're talking about translating a 1979 algorithm known as Cauchyon's ellipsoid method.
Okay, wow. So a pretty old school math problem.
Very. And by forcing these three totally distinct engineering philosophies to process the exact same mathematical truth side by side, this project uncovered some wild things.
Like what?
I mean, hidden bottlenecks, silent hardware failures, and these invisible math bugs that standard unit testing completely missed.
It's essentially using three different lenses to examine the same object, and suddenly seeing these massive structural cracks that you couldn't see with the naked eye.
Yeah, that's a great way to put it.
So if you are listening to this and you've ever wondered why software sometimes just inexplicably breaks, or how different coding philosophies impact the actual world running around you,
Right.
You are going to really appreciate this deep dive. But before we get into the hidden bugs, okay, let's unpack this. We need to understand the mechanism first. What exactly is this 1979 ellipsoid method mechanically trying to do?
So we are operating in the realm of convex optimization.
Okay.
Imagine you have this highly complex, multidimensional search space, and your goal is to find a single optimal point somewhere hidden within it.
Right, like looking for a needle in a multidimensional haystack.
Exactly. So you start by bounding the entire possible universe of answers inside an ellipsoid.
Which is just like a stretched out sphere, right? Or a multidimensional football.
Yeah, multidimensional football is perfect.
I've always liked the sculptor analogy for this kind of optimization.
Ooh, how does that one go?
Well, the algorithm is basically a sculptor looking at this giant block of marble. Every time they evaluate the stone, they use a cutting plane to slice off a massive chunk that they mathematically know does not contain the final statue.
Right. Yeah, that analogy holds up beautifully because of what happens after the cut.
What do you mean?
Well, once you slice away half the search space, the algorithm has to draw a brand new, tighter bounding box, like a smaller ellipsoid around the remaining chunk of marble.
Okay, to center the search again.
Exactly. And to calculate the dimensions of that new shape, the algorithm relies on these specific update parameters.
Right, I saw these in the notes. They are represented by the Greek letters rho, sigma, and delta, right?
Yeah, rho, sigma, and delta. And their values shift depending on the specific geometry of the cut you just made.
So the type of cut changes the math.
Totally. You could be making a central cut right through the origin, or a bias cut that's slightly offset, or even a parallel bias cut, which is slicing away two parallel edges simultaneously.
Okay, so we trap the answer in a shape, slice off the dead space, calculate a new smaller shape, and basically just loop that process until the shape shrinks down to our single optimal point.
That is exactly it.
But the real heavy lifting here, looking at the source notes, is this mathematical operation called a rank 1 matrix downdate. And it's a downdate because we are shrinking our covariance matrix, right? We're losing volume.
Right. The rank 1 downdate is basically the engine of the entire algorithm. It involves updating a matrix called Q, and it scales quadratically.
Which in computer science is noted as big O of n squared, right?
Yep, big O of n squared.
Mm-hmm.
Mechanically, this means the computational workload grows exponentially in relation to the number of dimensions you are analyzing.
Wow, okay.
So a 10-dimensional problem processes in a flash, but a 100-dimensional problem takes over 80 times longer to compute.
Oh, man. So the efficiency of calculating that matrix update is just everything.
Everything.
Which brings us to the three siblings tasked with running this heavy math, Python, C++A, and Rust.
Right. Our three subjects.
We have this delicate processor-heavy task, and I'm just fascinated by how these different languages attempt to abstract the math because their underlying philosophies couldn't be more different.
No, they're miles apart.
Like, Python is famous for being incredibly flexible, whereas Rust is famously unforgiving.
We see that philosophical divide immediately, actually, especially in how they structure the cutting planes we were just talking about.
How so?
Well, Python relies on abstract base classes and something called duck typing.
Duck typing. If it walks like a duck and quacks like a duck, it's a duck.
Exactly. It evaluates objects based on their behavior at runtime. If an object is passed into the function and it happens to have a cut method attached to it, Python just runs it.
So it doesn't strictly verify the object's pedigree beforehand.
Nope, not at all. Now, C++A, in contrast, utilizes C++20 concepts to resolve constraints at compile time.
Meaning it maps out the structural validity of the types before the program is even allowed to run.
Right. But then you look at Rust.
Yeah, Rust takes compile time checking to a level that feels almost paranoid.
It really does.
Like, in the source code, the developer used Rust traits combined with new type wrappers.
Yeah.
And I want to pause on new type wrappers because this is where the strictness becomes physical.
Oh, absolutely.
In Rust, a single cut and a parallel cut aren't just aliases for the same underlying data structure. They're completely walled off from each other in memory. You physically cannot mix them up.
You literally can't.
But my question is, does this kind of pedantry just slow down the programmer? I mean, is there a tangible benefit to building all these rigid walls when Python lets you just write the math and go?
Well, if we connect this to the bigger picture, that rigidity is what prevents catastrophic human error from ever reaching a live environment.
Okay, give me an example.
Imagine a tired developer accidentally feeding a single-cut data structure into a function that mathematically requires parallel cut data.
Yikes.
In Python, that structurally invalid object might slip right through the interpreter. The program runs, the math gets scrambled, and you output a totally corrupted answer.
But in Rust.
In Rust, the compiler treats that mismatch as a fatal error. It simply refuses to build the software. It forces the developer to acknowledge and resolve the logical inconsistency on their own machine.
Long before the code is ever deployed.
Exactly. Long before.
So it's like the ultimate gatekeeper.
Very much so.
But compile time safety only verifies that you typed the code correctly. It doesn't protect the math from behaving erratically once the program's actually running and, processing dynamic data.
Right. And that brings us to the first major discovery of this benchmark.
The danger of zero.
The danger of zero. This completely exposes the physical limits of computation.
How does that happen in our ellipsoid method?
Well, the math relies heavily on a value called omega. Omega represents the result of projecting your cut onto the search space.
Okay.
And nearly all subsequent calculations, like finding rho, sigma, and delta, they require dividing the data by omega.
Ah. And because it's dividing by omega, if omega hits absolute zero or even drops into denormal floating point territory, the hardware logic just shatters.
It breaks completely.
And denormal numbers, just to be clear, are those values so microscopically close to zero that the computer's standard floating point representation breaks down, right?
Exactly. They're basically a dead zone. So the software fundamentally needs a guardrail here. If omega drops into that dead zone, the code must abort the steps safely.
But the C++ implementation failed to do that properly, didn't it?
It did. The original C++ code had a really dangerous silent failure bug.
What did it do?
If omega was effectively zero, instead of catching the mathematical impossibility, it returned a status of success, but with zero displacement.
Wait, really? It lied?
It totally lied. It told the subsequent functions that a cut was successfully made when absolutely nothing happened.
That is wild. It's like the sculptor swinging the chisel, missing the stone completely, and happily moving on to the next step while logging it as a perfect strike.
That is exactly what it was doing.
But what blows my mind isn't just that a divide by zero anomaly exists. I mean, we've all seen those. It's that the ultra-strict golden child language, Rust, completely lacked the guardrails for it.
Yeah, Rust was entirely blind to the zero state in its original iteration. It possessed no guard check whatsoever.
None at all.
None. If it encountered a denormal omega, it just plowed right through the division.
Oh, man.
And in floating point computation, dividing by zero doesn't always crash the program loudly. Instead, it generates a state called nan.
Not a number.
Right, not a number. or infinity.
Yeah.
And those toxic values then cascade silently through the matrix operations, completely corrupting the entire ellipsoid.
And ironically, Python, the language we just criticized for being loose and flexible, survived this edge case natively.
It did. It handled the zero division gracefully due to his built-in exception handling.
Wow. But the ultimate resolution was updating all three code bases to recognize this denormal state and uniformly return a no-effect flag, right?
Yes. So the math stops exploding.
But Kachayan's algorithm faces a much slower, more insidious threat over time, which requires fundamentally changing the math itself.
Yeah, we are talking about numerical stability now.
Right.
When you update a massive matrix thousands of times in a loop, standard rounding errors compound. It's an inherent flaw in the floating point math.
Right, because computers can only hold so many decimal places.
Exactly. Over thousands of iterations, your pristine multidimensional football warps into this mathematically jagged, useless shape.
So how do you fix that?
To counteract this, you have to implement a numerically stable variant called the LDLT factorization.
Okay, I was looking at the source material on this LDLT factorization, and I have to admit, the math gets dense quickly.
Oh, it's very dense.
I know the goal is to stop those rounding errors from multiplying, but how does splitting the matrix into an L and a D actually achieve that stability?
Well, think of it like managing a massive multiplication problem. If you multiply huge numbers and try to store the final massive product, your calculator eventually runs out of decimal precision, so it rounds the number.
And that rounding introduces error.
Exactly. So instead of doing that, LDLT stores the building blocks. It factors the original matrix Q into a unit lower triangular matrix called L and a diagonal matrix called D.
Wait, so you are keeping the pristine prime components isolated rather than dealing with the messy rounded off total?
Precisely that. You maintain the mathematical purity.
Okay, that makes sense.
And to update the system, instead of directly multiplying the whole matrix, you use a technique called forward and backward substitution.
Which means solving for variables sequentially, right?
Right. It mathematically isolates the operations and prevents those tiny rounding errors from snowballing.
So what does this all mean for our benchmark? We introduced this beautiful mathematically safe LDLT variant, and it absolutely obliterates the execution speed.
It tanked it. The safety mechanisms introduced a massive memory bottleneck, especially in Python.
Why?
Well, to perform forward and backward substitution, the computer requires temporary workspace. It needs blank arrays to hold intermediate calculation values before arriving at the final output.
Like scratch paper.
Exactly like scratch paper. The problem was how the initial Python implementation acquired that workspace. Python was relying on heap allocation.
Meaning what, exactly?
Meaning it dynamically requested 5 brand new memory buffers from the operating system for every single call of the update function.
Wow. Every single iteration of the loop, it's asking the OS for new memory.
Every single time.
Imagine you are cooking a complex recipe with hundreds of steps. Python's memory strategy was the equivalent of driving to the store to buy a brand new mixing bowl for every single ingredient, using it once, throwing it in the trash, and driving back to the store for the next ingredient.
That is hilarious, but mathematically accurate.
Right. The math isn't what's taking so long. It's the constant trips to the store.
The overhead of dynamic allocation is just a massive hidden tax on software.
But Rust didn't do this.
No, Rust sidestepped this entirely by utilizing a scratch buffer strategy.
Right.
It pre-allocated the necessary arrays once at the very initialization of the program.
Just once.
Just once. During the thousands of loops, it simply overwrote those exact same memory slots. 0 new allocations were made during the active computation phase.
So it's just washing and reusing the 3 bowls you already own.
Exactly.
And the developer recognized this brilliance and decided to port Rust's memory strategy over to the other languages.
Right. They updated C++ to use 3 pre-allocated val array buffers. And they updated Python to use 3 pre-allocated numpy arrays.
And the performance leap was staggering.
It was huge. C++ achieved a 7.4 times speedup from that single architectural change.
Wow.
Its execution time plummeted to a blistering 22.5 microseconds, tying Rust for first place.
And Python.
Python's improvement was also massive, a 5.4 times speedup. It dropped from 4,400 microseconds down to 819.
Now, Python is still 36 times slower than the compiled languages, purely because of the overhead of its interpreter, right?
Right, that overhead is unavoidable.
But being 36 times slower is a total triumph compared to being almost 200 times slower, which is where it started.
Oh, absolutely. That memory fix proved that structural design patterns from a systems language like Rust can profoundly optimize a high-level scripting language like Python.
Okay, so C++ and Rust are now locked in a dead heat at 22.5 microseconds. They are memory efficient, they are guarding against zeros, and they are incredibly fast. But here is the ultimate question of the deep dive. Are these blistering fast algorithms actually outputting the correct answer?
And what's fascinating here is the sheer power of polyglot cross-validation.
Meaning what, exactly?
Because we have the exact same mathematical formula written in 3 distinct languages, we can run them through the exact same problem, specifically a benchmark called the Prophet-Oracle test case.
Okay.
And we can verify if they arrive at the destination in the same number of steps.
Here's where it gets really interesting. When running the Prophet-Oracle test using our safe LDLT variant, Python found the optimal answer in 83 iterations.
83 steps.
But Rust took 94 iterations.
94.
You would naturally assume the strict, hyperfast, memory-optimized Rust codebase was mathematically superior. But Python, the slower, dynamically typed language, was the one telling the truth.
It really was.
Python exposed a massive, invisible math bug that had been hiding in the Rust code for months.
This is the crux of why this benchmark project matters. The unit tests inside the Rust environment were all passing.
They were green across the board.
Green across the board. The software was returning a plausible answer without crashing. If this developer had only written the code in Rust, they never would have known the algorithm was taking an inefficient, corrupted path to reach the answer.
So how did the strict gatekeeper fail at the math? What was the actual bug in the Rust file?
It was a fascinating two-part failure in a file called lstable.rs. The first issue occurred during the back substitution phase we discussed.
The scratch paper phase.
Right. To aggressively save memory space, the Rust code was using the lower triangle of the matrix as a temporary scratch pad.
Okay.
But when executing the back substitution, instead of reading the untouched data from the original upper triangle, the logic accidentally read from the lower triangle.
Wait, it read from its own overwritten scratch pad?
Yes.
That is like sticking a Post-it note with your grocery list directly over the architectural blueprint you were supposed to be reading, and then trying to build a house based on the grocery list.
That's a great analogy. It fed corrupted data into the very next calculation.
And the compiler didn't catch it because structurally it was fine. It was just logically wrong.
Exactly that. And the second bug compounded the error. It happened during the Rank 1 update.
Okay, what was that one?
Kachin's algorithm relies on a Gauss-Seidel pattern.
A Gauss-Seidel pattern.
Yes. In computational mathematics, a Gauss-Seidel pattern mandates that as you calculate new variables, you must immediately use those fresh, updated values in the subsequent steps of the same iteration.
Oh, I see.
You maintain a running vector, let's call it V, that constantly evolves.
So you update your beliefs dynamically with the freshest possible data. You don't wait for the end of the day to process the new information.
But Rust failed to implement the running vector V error. It utilized constant stale values from the very beginning of the step. So you combine reading from the overwritten scratch pad with utilizing stale data, and the mathematical trajectory just drifts.
It drifted.
Yeah, it didn't drift enough to break the software violently, but it drifted enough to force the algorithm to take 94 steps to find the optimal point instead of 83.
That is terrifyingly insidious. The Rust compiler will scream at you if you use a string instead of an integer, but it is completely incapable of telling you if your Gauss-Seidel pattern is logically flawed.
Right, the math is invaluable to the compiler.
So what was the impact when they finally fixed these two issues in Rust?
Once the back substitution read from the correct upper triangle and the running vector V was properly integrated, the systems aligned perfectly.
Perfect match.
The maximum variance between the outputs of Python, C++, A, and Rust plummeted to an infinitesimal 7.34 times 10 to the negative 10th power.
Wow.
They were finally producing bit-identical results across the board.
That is incredibly satisfying. So to distill this entire deep dive down to a final scorecard for you listening, if you are architecting a complex system today, which tool do you choose?
Well, based on this rigorous benchmark, if your absolute priorities are safety, speed, and establishing a pristine reference design for memory management, you lean on Rust.
Even with the hidden math bug.
Even with the bug. Because Rust's architectural strictness forced the other two languages to elevate their game.
Fair point. However, if you require that same blistering speed combined with ultimate portability across older hardware, you choose C++.
Right. By adopting Rust's memory strategies, C++ matched its speed flawlessly at 22.5 microseconds.
And if you are prototyping or testing the sheer logic of the math, you use Python.
Definitely. Yes, the interpreter overhead makes it 36 times slower, but its readability and straightforward implementation served as the objective ground truth that exposed the invisible Rust bug.
This raises a really important question for everyone listening, regardless of whether you write code or manage people.
It's a masterclass in the dangers of a single perspective.
Absolutely. When we only analyze a complex problem through one framework, whether that is a single programming language, a single department at your company, or a single methodology, we become inherently blind to our own systemic errors.
Rust's internal unit test aggressively insisted the code was flawless. It required the external perspective of Python to prove it was drifting.
Validating your assumptions through a completely different paradigm is frequently the only mechanism we have to expose the invisible biases we bake into our own work.
Exactly.
Which leaves us with a lingering thought for you to mull over. If simply translating a well-documented 1979 optimization algorithm into 3 distinct languages catches critical mathematical errors that hundreds of modern unit tests completely missed, well, what other invisible math bugs are silently operating right now in the monolithic single-language software that runs our banking systems, our aviation networks, and our modern infrastructure?
It's a scary thought.
It really is. Until next time, keep digging deeper.